Hello everyone and welcome back to another video of the Hidden Quantum Champions. Today we are looking into cameras, a specific type of cameras, which is infrared cameras or cameras for different wavelengths. And Emberion, which is the company we are looking at today, is one of the leading players in this market that is pushing innovation and using quantum technology to make visible what has been invisible or not visible before. And if you want to understand what they are actually making in terms of products, how this is actually using quantum technology and what is interesting about it, or if you are already using cameras, for example, in surveillance, self-driving vehicles, medical market, inspection, like production type of inspection, then today's video might be right for you as we are diving deeper into Emberion. And with that, here we are as per usual on their website. And it says, disrupting image markets. Emberion develops and produces revolutionary infrared cameras that disrupt and extend multiple imaging markets. And we can learn more about that, but we will not do that for now. We will learn a little bit more about Emberion for now. So why Emberion? Today, most machine vision solutions mainly use visible spectra of light, and the machine vision market is affected and limited by high device price, and a single sensor solution covering both visible and infrared is required. Emberion extends the wavelength range substantially beyond visible light and offers imaging solutions at a significantly affordable cost. Now, a quick step back. So what are we talking about, right? So it is about machine vision. So that's basically a specific type of task. It is analyzing camera signals for some kind of process that could be, I don't know, a FaceTime. It could be a face unlock of your phone or your computer where it's detecting a specific face. Could be a self-driving car where a lot of different camera signals are coming in. Could be some application in terms of production where you are looking at, I don't know, quality inspection during the production. So these are all typical tasks in the field of machine vision. There are many, many more. And now the point here is that up to now, you're mainly using normal RGB cameras because these are cheap. These have been scaled up with consumer electronics. They are in smartphones, they are in computers, they are in cars, they're everywhere. They're produced in the millions, so they are cheap. On the other hand, there is the infrared spectrum, the infrared sensors. So when you are looking at, for example, thermal images, these are usually done using infrared cameras. These cameras, they are not so much mass market products, and the technology that is being used to create those is not really, let's say, something that is affordable. And that's why oftentimes when you're looking at these kind of, for example, night vision cameras that are using infrared, they are comparatively more expensive. And that also means if you want to enhance your computer vision task or your machine vision tasks, for example, if you are looking into production quality, you might be able, and we will see a couple of examples later in today's video, you might want to use additional wavelength in the spectrum to actually see stuff that with an RGB camera you cannot see. Look, the visual spectrum is actually divided into different paths. We start with the long wavelength usually, so low frequencies of light. These are infrared. Infrared is, let's say, on the low side of the spectrum. Then as we go up, we come into the visual spectrum. This is where we start with red light and we end with the violet lights, basically the whole rainbow, right? And then you are going up into the ultraviolet or extreme ultraviolet, which are the super short wavelength that are, for example, being used to create today's silicon, to create today's chips, which is, for example, what ASML is using in their lithography machines. So this is the whole spectrum. You can also go further up, then you come into the X-ray regime, where the radiation is almost aggressive already. So you might not want to, let's say, expose biological tissue to these. But of course, X-ray is also something that is being used in today's manufacturing lines to check for defects, for example. So there you have the spectrum. There's, of course, even further up energies, but we are not going to talk about these in today's video. But now we are looking at the low side of the spectrum, so these infrared type of wavelength. So revolutionary infrared cameras, so Emberion infrared cameras enable next level imaging and sensing. Made with patented nanotechnologies, our infrared cameras are suitable for demanding application areas including machine and night vision, where additional infrared wavelengths can provide significant advantage. Emberion solutions are ready to address challenges in various growing markets, such as industrial machine vision, enabling hyperspectral imaging, demanding surveillance, for example, defense and border security, autonomous vehicles, and medical imaging. And here you can learn more about the applications. This is Emberion, so highly cost competitive products with superior performance, extensive IPR protection, semi-fabless operation mode, and experienced and committed team. So semi-fabless is also an interesting wording that I think I have not stumbled across yet. So that just to quickly put that into frame. So there are semiconductor companies that have a fab. So they are manufacturing the silicon themselves. Not so many actually anymore today. Probably the most relevant or most well-known one is Intel. So they are still manufacturing part of their supply chain, or that they actually manufacturing still the chips themselves in their own fabs. Many other ones, like for example Nvidia, they don't do that anymore themselves. They just own the design, and then it gets, for example, manufactured at TSMC. But there are also other big players which are not as big as TSMC. TSMC is really owning a lot of the supply in that market, but there are also other players that do this manufacturing as a service, where you send your design and then they produce the chip. So these are usually considered fabless. Now, if you're semi-fabless, I assume that you are somehow in between. So you probably own most of the IP sitting in the design, not in the processes. I could imagine that semi-fabless means that you are still manufacturing huge parts of the chip somewhere else, and then you are kind of adding an additionally refining step on top in your own facility, for example. So our team has extensive skills and experience in nanotechnologies, graphene, and other two-dimensional layered materials, as well as high-performance industrial electronics. In addition, our R&D team, consisting of nearly 30 experts, Emberion's efforts are led by a strong and experienced management team. We operate from two R&D spots in hotspots in Europe, Espoo, Finland, and Cambridge, UK. Cambridge division has an extensive experienced team developing our sensor using nanomaterials with a state-of-the-art clean room and pilot production line. So I guess that's the semi part in fabless. And then Espoo division has been designing the electronics, CMOS, ROIC, integrating and characterizing the sensor and camera. Originally a spin-off from Nokia, Emberion was co-founded in 2016 by its employees and Verso Capital, a Finnish venture capital company. The chairman of Emberion's board is Mr. Anssi Kajola, I guess, managing partner at Verso Capital. And here we see the management team, and as you could probably already imagine from what was said before, this company has, let's say, the whole professional setup, so the CEO, CTO, and also the other managerial functions within the, let's say, top-level management or board of the setup. Then strategic partners and suppliers, so Emberion partners with leading companies in various application fields to solve market-driven challenges to address customer demands, and is the core player in selected world-class R&D initiatives. Emberion is a founder member of the EU FET or EU FET Graphene Flagship Project. The company is leading one of the spearhead projects and has preferred access to capabilities of the European experimental pilot line. Our world-class research include the following key partners, and then we have Cambridge, of course, so Cambridge Graphene Center, the Graphenia Amo GmbH, which is part of, or which is, I think, spun off from University of Aachen in Germany, and the National Laboratory in the UK, then the Technical Research Center of Finland, and the Defense Science and Technology Laboratory, UK Ministry of Defense. And then we see another couple of labels down here. I'm not going to go into the details of those, and some words here on the policy. And then as per usual, we see, let's say, the footer with both the locations in Finland, where the headquarters is in Espoo, and the Cambridge, UK office. Now, let's quickly check out the products. So as you probably already could assume from what we've seen before, they are in the space of cameras, right? So Emberion offers a selection of visible to short wavelength infrared, VIS and SWIR, and thermal imager products leveraging our core technology knowledge and experience to provide leading solutions. And then we see here the different products. So we see there's this camera, the V20 VS20 series with 400 to 2000 nanometers. Then we see here the core series, which I guess is then basically just the sensing core of that camera. So you could probably upwards integrate that into a whole camera, but this is if you want to create your own system around it. And then there's also some future developments mentioned down here, like for example the Emberion midwave infrared from 3 to 5 micrometers. So before we were talking about 400 to 2000 nanometers. 2000 nanometers is then 2 micrometers. And here we start from 3 all the way up to 5. So this is much longer wavelength. It's going much deeper into the infrared spectrum. These are the products that we can see here. What is probably more interesting for you as you're watching is what is the application of those systems. And I mean, here we see, let's say, the typical infrared type of applications where infrared plays an important role. One of them is machine vision. I mentioned that before. Think about some type of process monitoring tools that you might have. And here's also a couple of examples given: plastic cap enclosures, artwork, defects in packaging, but also semiconductor, wafer imaging, photovoltaic solar cell inspection. So that's also very interesting. If you apply, for example, a current to a solar cell, then you can see under the infrared spectrum that there might be cracks in there. So you can actually use that to figure out where there's defects in your solar cell. There's laser beam profiling, of course, especially for laser beams that are in the infrared spectrum, right? Then process monitoring and CMOS, glass and metal manufacturing. Here that plays a role because you might have reflections otherwise that you would only observe in the RGB spectrum. And then steel industry, defect of slag. That's for another discussion. Here's a couple of examples, and I think these are nicely visual. So here you see, for example, a plastic packaging with nuts in it. I think it's pistachio. And if you're looking at it from the visual spectrum, so this is a grayscale image here on the which you can see now, you can basically not see until which point this packaging is filled. But then if you drag the slider over here, this is now the infrared spectrum, you see the nuts are going all the way up until here, just as an example. And why is that the case? That's because this printing here on the plastic foil is actually transparent in the infrared regime and only absorbing in the RGB, in the visual wavelength spectrum. And I mean, this is very impressive. You can go also through these examples yourself. You can also see through and let's say differentiate different materials with this specific technology. And there are many other cases here as well. For example, autonomous cars, you see you might have a higher contrast if you're going to a different light spectrum. Medical devices, you can again look through the packaging. And there are other examples here as well, for example, in the surveillance range, where this might actually be an interesting add-on. And then, of course, there's thermal cameras. I was talking about that earlier on as well. Now, the interesting part, and this is, of course, why they are also part of the Hidden Quantum Champions, is because this is using quantum technology. This is basically a quantum sensor, of course, a very complex one, but it is using quantum technology to enable those measurements. And here it explains a little bit more how that actually works and what the composition of technologies is that Emberion is using to build these amazing cameras. So unique products created with patented technologies. Emberion professional imaging and photo detection products are based on unique technologies that integrate nanostructured optical absorbers, graphene transducers, and in-house designed CMOS circuitry. Emberion has developed a library of material solutions that enable creation of photo detectors for the full spectral range from visible to long wavelength infrared radiation. Selected material solutions enable monolithic integration on the top surface of CMOS wafers. Our team has created more than 100 patent applications in related technologies, and we have steadily growing IP portfolio. Our groundbreaking work has been reported in numerous publications in high-impact scientific journals. Emberion's innovation in the integration of CMOS electronics with novel materials, including the design and fabrication process, creates a unique value chain to create a highly efficient and scalable technology solution. Innovative pixel structure, patented measurement techniques and modes, CQD, so graphene photo diode devices architecture, and then the custom ROIC design for scalable pixel design up to 4K HD. Now here is where the let's say quantum part comes in. We are talking about nanomaterials and radiation absorbers. So Emberion's know-how for integrating optically absorbing materials with graphene transducers provides a versatile way of creating sensors and detectors on CMOS ROIC substrates for diverse applications. Emberion has optimized various processes and has developed device sensor structures using nanomaterials such as colloidal quantum dots and graphene. So here's a couple of images of that. So here you see the quantum dots, so these different dots here. And if you are zooming in, you can really, always stay hydrated, right? So if you're zooming in, so you see the scale by here, this is 5 nanometers, so it's very, very close. You can really see the subatomic orders here. You can nicely see the crystalline architecture of these quantum dots. This is probably a transmission electron micrograph, so recorded with a TEM. I will talk about SEMs, so scanning electron microscopes, and TEMs, transmission electron microscopes, in a future video. So if you want to learn more about that, stay tuned and subscribe to this channel. Now back to the quantum dots. So now we have this colloidal quantum dot image sensor diverge from conventional image sensors. And how do they do so? So these CQD devices are produced using wet chemistry, which makes their processing inexpensive and highly scalable. So wet chemistry usually means that you're using some type of chemical component. You might be spin coating that on top of your existing wafer, or by some other technique spreading that, and then you're using chemical processes. There's also dry chemical processes, or referred to as dry chemical processes, and clean room processing technology. That's usually, for example, when you're using gases to actually etch something. Let's go back to the text. So the wavelength range of photon absorption can be tuned and can be made very broad. Even the quantum efficiency of CQD devices is typically lower. The low noise of the CQD photodiodes compensates it, and the noise equivalent power NEP is sufficient for most of the applications. Then CQD SWIR image sensors can be operated at higher temperatures, reducing the system and sensor packaging cost. That's also kind of clear because of additional cooling and so on, right? Because if you are, let's say, able to work at higher temperatures, you need to take care less of the packaging, so how the chip is actually being packaged into the overall system, because you don't need to have something that is like super highly temperature conductive, because you can live with a bigger delta between the chip and, let's say, the outside of the chip where the packaging connects to the cooling, and that makes it cheaper in overall cost. And then based on possible direct monolithic integration on CMOS wafers, CQD pixels are scalable to small pixel size and high image resolution formats, for example up to 4K HD format. And then Emberion can scale its pixel arrays either down to very small pixel sizes or larger sizes depending on the application needs. Here it talks a little bit more about these, let's say, layer approaches, right? So you see these different CQD layers stacked on top of each other, and the different electrodes. You have the graphene, so the 2D layer in between. And here it says Emberion has developed sensor device structures and manufacturing methods combining nanocrystalline optical absorbers with graphene-based transistors, enabling photo detection from visible 400 nanometers leading to extended SWIR 2000 nanometers and ultimately to 2500 nanometers wavelength. Emberion's investments are focused on differentiating manufacturing processes, so photodiode processing, sensor packaging, camera assembly, testing and calibration. Our semiconducting nanocrystalline material enables convenient fabrication directly on standard CMOS wafers compared to the hybrid packaging process required for competing semiconductor heterostructure-based transducers. This is a major advantage that leads to improved yield, increased reliability, and lower manufacturing costs. Emberion employs different colloidal quantum dot materials that can be integrated reliably on graphene transducers and tailored to meet specific wavelength, range, and response curve requirements. And these are these different layers that you see stacked on top of each other here. Then quickly about the graphene 2D material, right? Graphene, I think we've talked about that before, is a carbon and atom network that is two-dimensional. You see these honeycomb structures here. This is basically what the graphene crystalline structure looks like, and you have in graphite multiple of these stacked on top of each other. In graphene you really just have a single one. Use of 2D graphene in image sensor pixels enables extreme simplification of the fabrication process together with significant improvements in noise performance and stability, enabling operation at higher temperatures. Emberion's technology can be utilized with highly sensitive graphene transducers, which detect the electric change generated in surrounding materials and convert the original optical signal into an electrical signal via a high gain amplification mechanism. So you would basically measure the voltage difference between those electrodes here, and then add an amplifier in between to actually amplify this into an optical signal. Let's see. Emberion's technology can be utilized. I think that one we had. So graphene transducers provide significant benefits to photo detector and sensor products as they can be fabricated directly on CMOS wafers, which means using single material platform technology. The key benefit is the ability to monolithically fabricate different graphene-based wavelength-specific detectors on custom-designed ROICs through low temperature post-processing. So you basically get the ASIC, you get the CMOS fabricated imaging sensor, and then via these low temperature post-processing methods, so basically chemical methods, probably like spin coating stuff on top of each other, but definitely not putting something in a furnace and heating it up, can basically produce these, let's say, on stacked layers on top, which then enable the let's say wider optical wavelength measurements. Then we see here custom CMOS ROICs. I think I don't need to go into the details of this specific one, but this is just, let's say, talking about how they do it in-house, how this semi-fabless manufacturing process works, right? Then on the system integration level, so Emberion sensor products are designed for easy integration with the customer's system using features of the ROIC and front-end electronics, so array multiplexing, analog to digital conversion, global electric shutter, high dynamic range imaging, adjustable amplification levels, noise reduction and other signal quality enhancements via correlated double sampling, custom design of front electronics and camera housing design with optimized thermal management. So basically the whole stack from, let's say, the software over the hardware integration, everything which they can basically help on. And then there's also an additional party on this pyroelectric materials-based sensor. I would assume that this is probably the next generation of sensors, but let's read in briefly. So Emberion is also developing MEMS devices in which a suspended pyroelectric substrate structure absorbs thermal radiation and acts as a modulator for the graphene transistor. These microbolometer devices are sensitive to MWIR and LWIR, so long wave and mid wave infrared thermal radiation, and can be tuned to be selective to specific spectral ranges by modifying photonics absorbers or antenna structures on pyroelectric film. So here we see what this would look like. You come in with the infrared radiation, and then you have here the pyroelectric substrate. As the name suggests, pyro as in like fire, electric as in electric, so changing heat into electricity, I guess very similar to a Peltier element, but probably on the smaller scale here, maybe on the micrometer or nanometer scale, I don't know. So that's a different kind of conversion mechanism that is being used to take the radiation and transform it into an electric signal. Then you see here these elements. You see here a gold produced gate. You see the two electrical connections here. There's a gate dielectric, and then there's the graphene channel that sits below this gate here, which I think is then kind of like a, I don't know, it's maybe like a high electron mobility transistor type of setup, which you use to detect this infrared radiation. Emberion is determined to solve challenges faced by the industry with its novel devices using nanomaterials in mid-wave range, and with its high-performance device enabling MWIR non-cryo-cooled. That's also probably important. You don't need to have a cryo cooler because that's, I think, how it's done today. Lower price of camera compared to existing, meet the specifications of applications requiring 3 to 5 micrometer detection, and then custom ROIC. Emberion is exploring various materials for its MWIR camera solution. I guess there are a couple of materials, right? So Peltier elements, for example, they exist already today. There are compounds, but these are probably not so easy to manufacture on these very small scales here. And that's what probably plays a role, because if you make it too large, this thing here, then the camera will be very, very slow because you need to heat up a lot of mass to actually measure something. Or it could also be very, very insensitive because you have to make sure that actually the effects that you are generating here, they are large enough so that you can actually measure, let's say, single photons or small amounts of photons that are hitting this surface here. Then there's also something here beyond the state of art, but I think that's probably it on the technology stack. Besides that, of course, there are also news available down here. I'm recording this in 2026, so March of 2026, and we see here the last one is from April of 2026, so very much up to date. There's always new stuff down here, and then also information about exhibitions that they've been presenting at. We have already seen everything about the company. That's how it opened up today, which means we are already at the end of today's video. If you liked it, please make sure to give it a thumbs up. If you are interested in general in companies from the quantum space that you might have never heard about before, also make sure to check out our playlist on the YouTube channel, which is called the Hidden Quantum Champions playlist. As always, make sure to stay hydrated, and I'm looking forward to see you in the next one. Until then, bye bye.